Imagine a game so complex that even the most powerful computers couldn't crack it for decades. A game with more possible positions than atoms in the observable universe.
That game is Go. For years, experts believed no AI could ever master it. The strategy space is simply too enormous for traditional algorithms like minimax or alpha-beta pruning.
Yet in 2016, everything changed. An AI called AlphaGo defeated world champion Lee Sedol, not by brute force calculation, but by using a completely different approach to decision making.
That method is Monte Carlo tree search, or MCTS for short, a search strategy that doesn't need human-crafted knowledge. Instead, it learns by simulating possibilities and statistically discovering which choices lead to success.
Games like Go have enormous search spaces, around 10 to the power of 170 possible positions. That is vastly bigger than chess. Traditional approaches like minimax and alpha-beta pruning simply cannot handle this scale. And because Go lacks a simple evaluation function, these classical methods fail, which led researchers to adopt simulation-based search, introducing Monte Carlo tree search.
MCTS is a best-first search algorithm that evaluates moves by simulating many random games. Instead of using a manually designed heuristic, MCTS learns from outcomes. Moves that lead to more wins receive more attention, while weaker ones get ignored. This lets the algorithm discover strategy by experience, making it powerful in domains where good evaluation functions don't exist like Go.
MCTS repeats 4 phases. First, selection, which follows the most promising nodes. Expansion, which adds a new state to explore. Simulation, which plays a random game to the end. And backpropagation, which updates nodes' values based on results. With thousands of these cycles, MCTS gradually identifies strong moves without any handcrafted knowledge.
In tic-tac-toe, MCTS simulates games from the empty board. Early rollouts show that corner moves tend to win more often, so the algorithm explores them more. Eventually, it learns optimal play simply from outcomes, demonstrating that MCTS discovers strategy through simulation, not pre-programmed rules.
MCTS must balance exploitation, choosing moves that currently look good, and exploration, testing less visited moves. This balance is achieved with the UCT formula, which gives a mathematical incentive to explore uncertain actions. This prevents the search from getting stuck and ensures broad strategy discovery.
MCTS became famous through AlphaGo, which defeated the Go world champion. AlphaGo used neural networks to evaluate moves and MCTS to search efficiently. Later, AlphaGo Zero learned purely through self-play, guided by MCTS achieving superhuman strength without human data.
Minimax search to a fixed depth and requires a handwritten evaluation function. It works well for smaller spaces like chess. MCTS, in contrast, expands only promising branches and learns from rollouts, allowing it to scale to extremely complex spaces like Go, where heuristics are hard to design. When we first heard about AlphaGo, we assumed it relied mainly on massive neural networks and raw processing power.
Yeah, but the interesting part is that neural networks alone wasn't enough. MCTS was the key place that allowed AlphaGo to search intelligently, not exhaustively.
Exactly. MCTS guided the AI toward promising moves, while simulations improved its understanding over time.
And that combination, learning and search working together, is what made superhuman Go possible. MCTS succeeds where brute force search fails, especially in large games with no clear evaluation functions. It learns through simulation, improves iteratively, and was crucial in breakthroughs like AlphaGo and AlphaGo Zero.